to my calculus students. How's everybody doing? I really do miss being with you in the classroom and sharing those interactions together. But I hope that you're staying positive, staying focused, and making the most of our current reality. I heard it said that life is 10% of what happens to us and 90% of how we react to it. How true that is for us today. The only question is, how will you react to this? Well, I wanted to reiterate to you my commitment to your education. I told you in the classroom that I take that very seriously, and I wanted to promise you that I'm going to give you my best to finish out this school year. Now, it's up to you to decide to do the same. Now, to help you with that decision, I've got good news for you. No, we're not going to watch movies till the end of the year, although I will show you a little video clip near the end. But the good news is that we made it to the last chapter of calculus. Yay! Guess what that means? That means one more assignment schedule. It also means one more test, and yes, we will do a test at the end of this chapter. But the chapter 7 that we made it to is the application chapter. It's the application of integrals. Now, an integral, remember, is the area under a curve, but the application goes a lot deeper than that. In fact, we'll find out that we can use integrals to actually find the length of a curve. We also will use them to find the volume of three-dimensional shapes. And in this first section, what we're going to do is we're going to learn how to use integrals to find the total accumulation of a rate. Now, it sounds a little fancy, but one of the most common rates we look at is velocity. And so you'll learn that when we do the integral of velocity, that we're actually accumulating all of those speeds. And when we accumulate those speeds, we end up getting distance traveled. Might sound a little familiar because we've actually talked about that a little bit, but we're going to dig a little deeper into understanding how integrals can help us to find the accumulation of rates. Now, to get started, what I want to do is actually take a look at this little word splash. What we have are some of the key words that surround the applications of calculus. Now, had we been in class, I would have had you make a couple sentences that intelligently connect these words and then share them with your classmates. Going to be a little tricky to do that now, but would you still think of a few sentences? Look at these words. How could you make a calculus connection between them? And I'll meet you back here in a few moments with your sentences. All right, so what are some of the popular sentences that you thought of or that you should have thought of? Well, probably one of the most common ones is that the derivative is the slope of the curve. That's a great one. That is definitely true. Now, make sure you know that the integral is the area under the curve. That's where we've actually been for the last couple months. Now, you get some of these other physics words in here. Maybe you remember that the slope of position, or maybe you said the derivative of position. Well, that would equal velocity. That's a really good sentence. And maybe you took it a step further and said that the derivative of velocity is equal to acceleration. That would definitely be true. But that's from the first half of the year. What about the antiderivative? What about the integral? Well, we have this major idea that the integral of velocity, the antiderivative of velocity, that would actually take you back to position. And when we talk about that, we also throw in this idea that the integral of velocity will help us to get distance traveled. And that's exactly where we want to start now by looking a little more closely at our physics calculus ladder. Now, this would be a great diagram to add to your notes. If you haven't taken out any notes yet, I encourage you to do that because we've actually been climbing and playing around on this ladder all year. But what we're going to do today is we're going to very nicely tie this all together. You see, we could say at the top of the ladder is the position function. The position function has been called S of t as we've been together in class. But to move, we'll say, down the ladder, we can do the derivative of position. And the derivative of s, the derivative of position, well, that's going to give us velocity. And, of course, velocity we've been calling the v of t function. So if we do the derivative of position, we move down to velocity. Well, it doesn't stop there, right? Because we could do the derivative of velocity. Move down another rung, and we'll get to acceleration. So the derivative of velocity is acceleration. Now, those are all things that we learned in the first half of the year. But what we want to do now is we want to go back up the ladder. We want to make the connection that we can do the integral. We can do the integral of acceleration. And when we do the integral of acceleration, that is the antiderivative, then we will get to the velocity function. And of course, we can do the integral of velocity, and this is what we kind of talked about in a little word splash. We can do the integral of velocity, and that'll take us back to the position function. So what does this mean one more time to say that the derivative of position gives velocity? Well, remember, it means that the slope of a position graph, the actual tangent line, is going to describe the velocity. It's going to describe the velocity of that moving object. And what does it mean, one more time, to say that the integral of velocity is going to give position? What does that really mean? Well, now we use the word area, and it means that the area under a velocity graph, well, that will give area under a velocity graph, well, that will give the distance traveled. Okay, now you've heard both these ideas. We just wanted to kind of tie them all together, and that will be our primary concept that takes us through this first section of this chapter. That is, that if you do the integral of velocity, you're going to get a position function. Now, the position function can give us position, and it can also help us to get the distance traveled. What we're going to need to do is be real careful about understanding what the question is asking us to find and what the integral actually does. But again, the integral of velocity will give us the position function. And that's now what we're going to do is we're going to apply that with some classic integral application problems. All right, so here we have a velocity equation. 3t squared minus 18t plus 24. Now, what that does is that describes how fast a particle is moving along the x-axis. Something that you have to understand here is that the particle very well might be moving forward and backward. Maybe it moves to the right. Maybe then it turns around and moves to the left. Maybe it moves to the right some more. So that's the movement of this particle. This equation, this velocity equation, is describing its rate as it does that. Now, we want to find the particle's displacement. Already, we're jumping into one of these fancy motion words from physics. Displacement is always the final position minus the initial position. And there we have the word position. So whether you understand, whether you took the physics last year or not, what you want to understand is that when we do the integral of velocity, we're going to get the position equation. In other words, we definitely want to do the integral because we want to get position. All right, so remember how to do the integral? You add to the exponent, you divide by the new exponent. That's kind of nice to give us t cubed. It looks like you're also going to end up with 9t squared because you're going to divide by 2, and you get 24t. Now, students sometimes will ask, well, what about the plus c? Well, before we answer that, I want you to think a little bit about what this is asking you to do. Again, it's asking you to find the displacement, and displacement is a subtraction problem. Well, where have you done a subtraction problem involving an integral before? That's right, you've done it when you've integrated from a to b. You see, ultimately for this problem, we're going to end up doing the integral from a to b of v of t. And of course, that's going to be like finding s of 4 minus s of 0. That's going to be our displacement because the subtraction is built into the integral. So we don't need the plus c because we're going to be subtracting. But more importantly, what I want you to realize is that to find displacement, the subtraction is already built in to my integral. So the only thing left to do here is to find s of 4 and, of course, s of 0 and subtract. Now, plug 4 in. Make sure you're plugging it into the t cubed t squared 24t equation. I'm going to just show you that that number comes out to be 16. Now, plugging in 0 is pretty easy because that's going to come out to be 0. So we end up with 16 minus 0. We end up with 16. Now, what you want to understand is that that represents the total change from my starting position to my final position. You see, I actually started at 0, and I actually ended at 16. But that means that I changed by a distance of 16. And I guess it's 16 feet because of the way this problem is worded. Ready for our next question? What we want to do now is we want to figure out when the particle is moving right, left, or stopped. Okay, now, this is not a position equation because the idea of moving is a velocity. When I'm moving, I have velocity. So you might say this question is really asking, when do I have positive movement? That would be to the right. When do I have negative movement? That would be when I'm going to the left. And when am I stopped? When I'm stopped is when I have 0 velocity or 0 movement. Okay, so to answer this question, we're going to appeal to a graph. Now, the graph that I'm going to type in the calculator is the velocity graph. And this would be a great opportunity to use your calculator. You're going to have to do this a little bit in your assignment and type in the actual velocity equation that you see here. Now, you would type that velocity equation into the y equals screen, and you might need to adjust your window to get a little bit more, a little more y max. Make your y max go up to maybe 25 or 30, and you're going to end up seeing a graph that looks like this. Now, this is a velocity graph, and I know for some of you it brings back some memories from your physics class. But what we want to do is we want to understand what this graph is showing us. And quite simply, it's showing us velocities. Like right here in blue, it's showing us positive velocities. Like right here in red, it's showing us negative velocities. Quite simply because it's below the x-axis. And right here in purple and right here, it's showing us 0 velocity. And if you did look at this closely on your calculator, you would see that you would have known that these two spots are at 2 and 4. So when is the particle moving to the right? Well, it's moving to the right between x equals 0 to x equals 2. When is the particle moving to the left? Well, it's moving to the left between 2 and 4. Notice that those are the x-intercepts. And when is it stopped? Well, it's stopped at t equals 2 and 4. Now, if you look at this last question, we're asked to find the total distance traveled. The total distance traveled. And so now we're back again to this word distance. And what we want a student to understand is that distance always involves the antiderivative of velocity. But since this problem is asking for the total distance, we're going to have to subdivide. We're going to have to subdivide so that we can absolute each of these integrals. You see, when I have positive velocity, I am moving to the right. When I have negative velocity, I'm moving to the left, but I can still think of that as movement. And so what this question is really asking is for the total movement. So we will do the integral, we will do the integral because the integral velocity always gives us a position. But in this case, I'm going to have to split it and go from 0 to 2, and then go from 2 to 4, so that, again, I can think of the absolute value of each of these separate distances. Now, keep in mind that each of these is going to give me a displacement because I am subtracting, and that's exactly what you have to do to compute the answer to this. You're going to have to find s of 2 and s of 0, and of course you're going to find s of 4 and s of 2, but ultimately I'm going to subtract these numbers so I can turn these into actual displacements, actual amounts of movement. Now, when you plug in 2 to that s equation, you get 20. What that really represents is that after 2 seconds, I am at a position of 20. Of course, when you plug in 0, you're at a position of 0. If you subtract these numbers, you obviously end up with 20. Now, we already figured out what happens when I'm at s of 4. S of 4 means I'm at a position of 16. And of course, we just found that s of 2, we were at a position of 20. Look what happens when you subtract these numbers. You get a negative displacement. Now, that should make sense because I was moving backwards. It was negative velocity. But the good news is I can just do the absolute value of these two numbers and end up with my total movement, my total distance traveled. And that, of course, ends up to be 24. 24 feet, technically, because of the units in this problem. But that's our total distance traveled. All right, now had we been in class together, this next problem would have been one that I would have encouraged you guys to ponder. No, it's not exactly the one that we just did before, but there are some likenesses, and there's something here I want you to see if you can figure out. If I give you the velocity, and I also give you an initial position, could you use that information to try to come up with the particles? We'll call it the particle's final position after 6 seconds. This is a great time to pause the video to actually think about how to do this. Yes, when you come back, I will work out the answer with you. All right, did you actually think through the problem, or are you just letting the video play? I do mean it that your willingness to think about this on your own is going to help you to figure out these problems when it comes time to do the assignment. Well, if you did the integral, that honestly, I would have expected you to do that. That is definitely needed because the integral gives the position equation. Even if you're not sure about the final answer, you have to be sure that it has something to do with position. So, yes, you end up getting 2t squared plus t, okay, unless you use the x's. But what does that represent? Well, remember that equation represents the position of my object after t seconds. And it says here that I have this initial position. It's kind of like I'm starting at the 3-yard line. How do I make this equation start at the 3-yard line? Well, yes, you have to put the c value in. And in the case of this problem, what I've really done is I've given you that c value. I've given you that initial position. And so the good news here is now I can just plug in 6 to my new and improved equation, the one that has the plus 3. And when you plug that in, well, you're going to square it, you're going to add it, and you're also going to have this plus 3 tacked on. That ends up giving you 81. Now, what I want you to understand is that 81 is not the distance I traveled. Rather, it's the position I'm at after 6 seconds. Okay, so 81 is a position. This question does not ask me to find a distance traveled, but if it did, all I'd have to do is subtract my final position this is the displacement now, and displacement is like the distance you traveled. So all I'd have to do is take my final position, which is 81, and subtract with it my initial position, and now that would be a different kind of number. That would represent how far I went. Okay, so 81 is my position. 78 would be my displacement, had I asked you to find that. Ready for another question? Now again, honestly, if we had been in class, I would have asked you and suggested that you try to figure this out on your own. So here we have a acceleration equation. Here we have an acceleration equation. And notice that the question is obviously asking you to determine the velocity. And of course, there's some initial velocity that's also given of 5 miles an hour. Great time to pause the video, see if you can determine the velocity of this car after 8 seconds. All right, now if you did the integral of this acceleration equation, you're understanding that ladder diagram that we had, because the integral of acceleration is going to give velocity. Okay, so that is definitely a yes. You have to change this to a t squared, and when you divide by 2, you end up with 1.2. And are you catching on that the 5 is actually the initial velocity, in other words, the c value? So we've got ourselves a velocity equation, and I hope that you plugged 8 into it. And when you plug 8 into this v equation, you end up with 89, almost 90 miles an hour. Okay, pretty straightforward. That would be the velocity after 8 seconds. But what about if now I asked you to determine the car's displacement after 8 seconds? Okay, here we are again throwing this word displacement around. Well, remember, displacement has something to do with position. It's the change in position. So now what would you do? Good time to push pause, see if you can figure it out. All right, now if you're trying to do this on your own, a great thing to do would have been the integral of velocity. Of course, when you do the integral of velocity, it at least takes you to the right level of the ladder. It takes you to the position equation. Now, that's going to give you a t cubed exponent. Of course, you also have to divide by 3. It's also going to give you a squared t squared exponent, but you have to divide by 2. And we also get a t beside the 5. Now, if you're saying, I'm not sure, should there have been a c value? Well, remember, the c value would be the initial position. Nothing over here has given us the initial position, so I don't have a c value. And the reality is I don't need a c value, because since this is a displacement question, it's actually asking me to subtract. And so built into the integral of velocity from 0 to 8 is the implication that I'm going to be subtracting. I'm going to be subtracting s of 8 with s of 0. Now again, if we were in the classroom, a lot of times students will ask, what does this really mean, s of 8 minus s of 0? And quite simply, it means that we are subtracting 2 positions. Now, when you subtract 2 positions, you get displacement. So what we want to do is we want to find the position at 8 and at 0. Of course, that just means that you're plugging in to your s equation. You'd be plugging in for each of these t's. That'd be something to do. I'm going to give you the answer here, because when you plug it into the first one, you get 276. Now, with a decimal, 276.8. And when you plug in 0, you get 0. Interesting. If I subtract those numbers, it appears that I get 276. Now, what 276 what? 276 miles, since this is miles per hour? I doubt it. This is only 8 seconds of acceleration. So, maybe it's 276 feet. Now, here's where we're getting into a little bit of an issue with labels. And I'm going to tell you, and then I'm going to show you why, that what you need to do is you need to divide, first of all, this answer by 3,600. Now, 3,600 is not just a random number. It is how many seconds are in a hour. Because what's really happening here is this problem started out in hours, but we are plugging in seconds. And again, there's a little bit of like a unit mismatch that I'm going to show you, but let me first just tell you that when you divide by 3,600, you end up getting 0.07. Now, 0.07 would actually be miles. Okay, the only problem is we don't usually walk around talking about 7/100ths of a mile. So if we would like, we could multiply that by 5,280, just 5,200, because that's how many feet are in a mile. And what we can do is we can kind of convert this into feet, because that's just a number that makes a little more sense to us. And so we end up traveling 405 feet over 8 seconds. Now, whether you realize or not, that's a little more realistic when it comes to a velocity and acceleration that was given in this problem. So why did we divide by 3,600? Well, to answer this question, we're going to take a little trip deep into the caverns of calculus. Now, in all seriousness, this is a little theoretical, but I believe that you can understand it, and I'd like to present it to you carefully by thinking about position, that's our S, velocity, and acceleration, the latter that we started with. Now, if you took a physics class, and even if you didn't, you could probably agree with me that velocity is often measured in meters per second. That's a very common way to describe velocity. And, of course, position can often be described in meters. Now, acceleration is often described in meters per second squared. What's really happening with these units, with these labels? Well, if you think about it, to go up to meters, what we did was we multiplied by seconds, because when you multiply by seconds, you cancel out the seconds. How about this meters per second squared? Why is that really happening? Well, what's really happening is when you do the antiderivative, when you do the derivative, what you're really doing is you're dividing by seconds. And when you divide by seconds, that gives you a second squared. So how about for our problem? Well, for our problem, we started with miles per hour. We started with miles per hour because that was the velocity that was given to us. Now, you might say, Ms. Naylor, no, we really started with the acceleration. Well, that's fine. That is actually what was given, but we were never given that unit. But if we did, then we would have had to divide by s. This is kind of weird, but if you divide by s, you get miles per hour per second, and that would be the acceleration of that original equation. But what I really want you to understand is, what is the position measured in? Well, you can't just say the position is measured in miles, because it's not. Because what's really happening is we're multiplying by seconds. So therefore, it's measured in miles seconds per hour. Yes, miles seconds per hour would actually be my position. Now, that's a goofy position, but what that means is that that answer we had of 276 was actually 276 miles seconds per hour. And so what we want to do is we want to cancel these labels. We want to cancel the label of hours and seconds so that we can be left with an answer that's actually something we do understand, which would be miles. I'm getting a little ahead of myself, but let's cancel these labels. Let's cancel hours. So we can say that in 1 hour, there are 3,600 seconds. You see, that's where that number came from, where I end up dividing by 3,600, because I can cancel these labels. So when we finally divided by 3,600, we got an answer that was in miles. But of course, it got converted. It got converted to be that 0.07 number. But that 0.07 number was actually in miles. Okay. Now, when you do a problem like this in your assignment, you can just divide by 3,600, and it'll work. but I want you to realize that it's because of these labels. So we just got done analyzing some equations. What now if we want to analyze a graph? Now I understand that graphs sometimes get kids a little worked up, but let me help you understand. This is a velocity graph. Now, because this is a velocity graph, the area under this velocity graph is going to represent a distance traveled. So this 11 right here, this would be like how far you traveled from 0 to A. You might think of it like you took 11 steps forwards. Now this 5, this would be like the distance you traveled from A to B. But since this is under the x-axis, this would be like a negative distance traveled. This would be like taking 5 steps backwards. And so this 4 is like taking 4 steps forward. So each of these circled numbers, it's an area, but it represents a distance traveled. So if I want to answer the question about displacement, displacement is simply the change between my starting position and my ending position. Now, if I start at 8, and I take 11 steps forward, now I'm at 19. Okay? If I then take 5 steps backwards, let's show this. If I then take 5 steps backwards, now I'm at 14. And if I take 4 steps forwards, now I'm at 18. Now, be careful. 18 is where I'm at the end of this adventure. But since I started at 8, I have to subtract that. So displacement is always your final position. What was that final position again? 18. Minus your initial position. And so that means I have displaced a total of 10. I have changed by 10. Now, if I want to know the total distance that I traveled, that is not a displacement question. That's not the change. The total distance is really just adding up all the steps I took. So, of course, in an absolute sense. So you take 11 steps, and then you take 5 steps, and then you take 4 steps. Now, the reality is that each of these numbers has to be thought of as an absolute value. Okay, because it doesn't matter if I'm doing positive or negative steps. But the reality here is that I ended up with a total distance of 20. Okay, because again, I'm looking at the absolute distance I traveled. By the way, that answer did not use 8, okay, because it's not a position question. Speaking of positions, that's exactly what these last 3 questions are. It's asking you for the position after A, meaning after A amount of time. Well, I start at 8, so I have to use that position number again, and I move 11 units. I feel like you've seen this answer before. That means I'm at a position of 19. Now, to do letter B, I have to just take my 5 steps backwards. So my position after B is going to be 14. That's the position after B. Oops. The position after A. The position after A is 19. And then my position after C, well, that's going to take my 4 steps forward again. And you actually have seen this answer before, but that's 18. My position after C is 18. I really want you to see how all 3 of these questions were different. So to say it again, the first one here was about displacement. Displacement is the change between my final position and my initial position. Total distance is how many steps I took in an absolute sense. And then this last one, position, the position is just takes into account where did I start and where am I after I move steps forward and backward. You're going to have an exit ticket that's going to use some of these ideas to help you to answer that question. But before we do the exit ticket, I want you to think about one more idea with me, and that honestly is the big idea of this section, and that is that we are accumulating rates. You see, whenever you do the integral of a rate, you always get the total accumulation. So we've done the integral of velocity. That's like accumulating a bunch of speeds. In other words, finding the position or the distance that you travel. But what if I wanted to integrate a different kind of rate? Like maybe I wanted to integrate money. Now, to make money a rate, it would have to be like money per month. Well, if you integrate how much money you make per month, you would get the total money you make over maybe like 12 months, over like a year. So we can integrate a money rate. What if I wanted to integrate like a population rate? Like maybe the way that a population is growing per year. Well, if I integrate over so many years, I'll find the total population after that many years. What you want to understand is that when you integrate a rate, you always get a total. Now, that is always the case for any integral of any rate. It will always give you the total accumulation of that rate. And I want to show that to you through two more problems that they do not have to do with velocity rates. So take this rate, for example. It's kind of a strange rate, but it's the rate of potato consumption. And so potatoes are being consumed at a rate of 2.2 plus 1.1 to the t power millions of bushels per year. Now, it took me a while to understand this the first time that I read the problem, but what we have to understand is that this equation is a rate equation. So we're going to have to integrate. You always integrate a rate. And that's because what we really want to find is the area under this rate graph. Now, since we're trying to find how many bushels were consumed at the beginning of 2002 to the end of 2003, we have to understand what our limits of integration are. And since the beginning of 2002, we can represent that with a 2, but the end of 2003, that would not be 3, because that would only be 1 year of potato consumption. Instead, what we have to do is we have to go the whole way to 4. And when we go to 4, what's really happening is we're getting 2 years of area. Okay, from 2 to 4 is actually 2 years of area. So yes, I'm going to integrate this potato formula. When I integrate it, using the rules that we've learned, add to the exponent. Now, 1.1 to the t power, that's an exponential. Since it's exponential, that's going to give us the same thing, but remember you have to adjust it by dividing by the ln of 1.1. But here's what I want you to understand. This formula here, this new formula that I got, this now is a formula that will give us the total. I'm going to just call it T, because the C is already capital. But this is the antiderivative, so it's going to give me the total when I plug into it. So that's what we're ready to do. We're ready to plug in 4. We're ready to plug in 2. And I'm sure you can guess that we're going to subtract. Now, I know you can do this, but the thing that is often confusing for students is why. Why do I have to do this? And to say it again, that's because this equation I gave you is a rate equation. And whenever you have a rate, you integrate. So you can get the total. Okay, now 24, I guess it would really be millions of bushels. That represents how many bushels were consumed in 2004. And of course 17 is 2002. So if you subtract these numbers, you'll find the area represented in between these two. So when I write down the number, what are we going to get here? When I write down the number 7.1, that's going to be millions of bushels not per year, but millions of bushels for those 2 years. And that will end up being the area that was under our curve. If we were in class, sometimes students will say, why can't you just add? Why can't you just add these up? And the reason I can't just add up 3 numbers is because I want to get an area. And the area represents all the numbers between 2 and 4 to give me that total consumption. All right, so the last problem we're going to do, and it has to do with a rate, is actually in your book on page 369. I encourage you to get your book out, open it up, take a look at example 6. It has to do with a pump that is pumping, I guess, water, but it operates at different rates, maybe because different load on the pump, maybe because of different amounts of voltage, but there's these different rates that are recorded. And what we want to understand is that, as the book is asking, if we want to get the total consumption of water, basically the total gallons that are pumped, well, as we've done a couple times here, we're going to need to integrate. So what we want to do is we want to integrate these rates. Now, if you're saying, yeah, how am I going to integrate rates that are written in a table? Well, remember, the big picture here is that table is actually representing a graph. And this graph that I'm drawing here quickly may not be the exact, match the data exactly, but the point is that there is an area under this graph. So the question really is how do you get the area? Because remember, area is the same as an integral. And the answer is trapezoid rule. We're going to use the trapezoid rule to integrate these data points. And it's actually quite easy to do as long as you remember the trapezoid rule. And the trapezoid rule always requires an h divided by 2. Now remember that h is the length of your interval. If you look at the data carefully, you can see that the intervals are all in minutes, 5-minute intervals. And then the rest of the trapezoid rule, I hope you remember, is really just adding up the y values. Now the y values would be these rates. Of course, you use the y values in between twice. So I double those until I get to the last one that is only used once. Technically, you would add all the numbers together and multiply by 5 halves, and that ends up giving you 3,582 gallons. Now, this problem does not need to be divided by 3,600 because the whole thing is in minutes. The rates are in minutes, and my integration was done in minutes. But the real point here is I want you to understand that this 3,500 number is actually the area that's under this rate data. And anytime you integrate a rate, you always get the total accumulation. I'm going to be completely honest with you. This is not an easy section. Had we been in the classroom, I would tell you the same thing. And of course, being apart does not make it any easier. We're doing word problems. They have to do with physics. And there's a lot that you're trying to put together. I'm sharing this with you, though, because I want you to focus. I want you to try. And I want you to succeed. And this exit ticket is your first step in getting to that success. There's some skills here that I'm trying to get you to think about. There's a few things that you have to put together that I did in 2 separate problems, but you're trying to put them together into one problem. And you're going to want to turn this in before you really get too far into your assignment, so I can give you some feedback. Now, I'm going to give you some thoughts, but I don't want to give it all away. First off, I want you to notice this is a velocity graph. The reason I say that is because the area under a velocity graph is important, and you can bet the bank that this problem has something to do with finding area. Of course, keep in mind that we have positive and negative area, so that is going to come into play when you start thinking about if you're moving forward or backward. Now, the other thing, and the main thing that students usually have trouble with, is understanding what is it that I'm really asking. And what I'm really asking is that you find S of 12, but I'm going to be nice to you and tell you that means I'm asking you for the position. I'm asking you for the position at 12. That means after 12 seconds of moving forward and backward and forward, where are you? What is your position? And yes, that's going to have something to do with your initial position, because if I start at the 5-yard line, that's going to affect where I end up after moving forward and backward. Okay, so take it from there. You're allowed to talk to people about it. I want you to turn it in. I will give you feedback, and with hopes of getting you guys ready then to successfully do your assignment.